Bismillahirrahmanirrahim. This lecture is about transformation of strain components. In this lecture, we will discuss about transformation of strain component, its analytical derivation, and then a, a relation between strain and stress Mohr circle. So let's start from it. For transformation of strain components, stress-strain relation. We already know that stress-strain relation defined by Hooke's law permit us to estimate the stresses from strain that can be measured. In this article, we study the transformation of a given set of strains into principal strains. For example, consider now an element which is being subjected to the general state of plane stresses shown in figure. The normal stress is assumed to be tensile, which elongates the element in the x and y direction, and the shearing stress distort the element through shearing strain gamma xy as shown in figure B. Let this be the element with dimensions dx dy with a plane stress element sigma x, a tensile stress acting in the x direction, sigma y tensile stress in the y direction, and similarly tau xy and tau yx. This is the inclined plane which is at angle theta. We have cut this element. For example, this is an inclined element OA, and this plane is known as U and this as V. And similarly, shear stress which distort the element through a shear strain gamma x y. So let's start. As we know that strain is equal to change in length divided by original length, and this change in length will be equal to strain multiplied by the original length. The effect of these strains on any line element OA is shown in figure. For example, we have an element OA. When we apply the stress sigma x, there will be a strain in the x direction, and let this strain be equal to, or let this change in length will be equal to this sigma x will try to elongate this element, and this will change the length, which is the change in length will be equal to ex into dx. Dx is the original length where ex is the strain in the x direction. Similarly, when a stress applied in y direction, it will try to elongate the element in y direction, and a change in length sigma y dy will be produced. Similarly, when shear strain acts gamma xy, this will distort the element in this direction. A change in shear strain is equal to gamma xy into dy. Now we need to uh, determine that what is the change in length occur in the direction of OA, and what is the angular change occur in the which is perpendicular to the OA. For example, the magnitude or change in length of OA is found by projecting ex dx, ey dy and gamma xy dy upon the direction of OA. हम क्या करेंगे कि suppose this is an element OA. Now it has been changed to an element OA dash. So change in length is AA dash. We will draw the components of it. This change in length, a parallel component and a perpendicular component. A parallel component will give you the change in length, whether it is increasing or decreasing, and this perpendicular component will give you the change in angular. This will give you the angular deviation, angular change. Okay. So let's suppose for this AA dash with an angle theta, this horizontal component will give you ex dx cos theta, means this length is ex dx cos theta, and this perpendicular component will become ex dx sin theta, and the angular change is beta 1, which has been from A to A double dash. Okay. Similarly, when sigma y stress applies, this element changes from OA to OA dash, and this angle theta, this parallel component which gives you the change in length is equal to ey dy into sine theta, and this perpendicular component which is actually in the perpendicular direction to the A point OA, this will give you ey dy cos theta. Similarly, this angular change gamma xy, this will give you um, like this gamma xy dy sin theta and gamma xy dy cos theta, and angular deviation is beta 3 beta 2, and this inclined length is equal to ds. So the total magnitude of change in length of OA is found by projecting this ex dx ey dy and gamma xy dy upon the direction of OA. So delta D will be equal to what? Ex dx cos theta. We will add all those components which are in the direction of OA. So ex dx cos theta plus ey dy sin theta minus gamma xy dy cos theta. Now divide both these sides with a inclined dimension ds, delta d by delta s. This will give you actually the value of strain, and this ex dx by ds cos theta dy by ds sin theta minus gamma xy dy by ds cos theta. This dx by ds, if you see this element, this dx by this ds will give you base divided by hypotenuse will give you a cos theta. So this will become cos square theta. This perpendicular divided by base will give perpendicular divided by hypotenuse will give you the sine square theta, and this will give you sine theta. This, so your equation will become like this. Suppose the strain at any particular point for OA will be equal to Ex into what is cos square theta. Cos square theta is equal to 1 plus cos 2 theta divided by 2 plus Ey into 1 minus cos 2 theta divided by 2 minus gamma xy sine 2 theta divided by 2. So ultimately you will get the equation in this form. Now we will go to the angular deviation. The angular deviation of OA, i.e. beta, is determined by dividing the perpendicular components of AA dash with the original length ds of OA. अब हम perpendicular components को divide करेंगे original length पे OA के साथ. बीटा किसके बराबर हो जाएगा? ex dx divided by ds sin theta minus ey dy divided by ds cos theta minus gamma xy dy divided by ds sin theta. आपके पास ये जो गैमा एक्स डी वाई की वजह से, इसकी वजह से, क्योंकि गैमा की वजह से शॉर्टनिंग हो रही है, इसलिए इसके साथ हम माइनस यूज कर रहे हैं. तो बीटा की वैल्यू सिमिलरली वो एंगल्स की वैल्यू पुट करें, आपके पास ये एक इक्वेशन बन जाएगी बीटा की. नाउ फॉर द एलिमेंट which is on the right angle to the OA, the angular deviation beta dash may be found by substituting the angle theta plus 90 degree for theta. Since we know that sin theta plus 90 is equal to cos theta and cos theta plus 90 is equal to minus theta, so putting this value in the equation, your beta dash will become this minus ex sin theta cos theta. We have put the angle theta plus 90 degree and change the trigonometric identities, and we will get this equation B. From this equation A and B, we have came to know that beta and beta dash rotates in opposite direction. So their absolute sum or their sum is equal to their algebraic difference. क्योंकि इक्वेशन से आपको पता चल रहा है कि आपके पास जो इक्वेशन A और B ये शो कर रहे हैं कि बीटा और बीटा डैश ऑपोजिट डायरेक्शन में रोटेट कर रहे हैं, इसलिए जब इन दोनों इक्वेशंस को आप ऐड करेंगे तो ये एक्चुअली आपको क्या देंगे? अलजेब्रिक डिफरेंस देंगे. हेंस जो टोटल चेंज है in the right angle between OA and its normal OB, which defines the shearing strain for an element located from theta from xy, located at an angle theta from xy, becomes, so change, shearing strain, change in angular deviation will be equal to beta minus beta dash, put the equations, and you will ultimately get an equation gamma is equal to ex minus ey sin 2 theta plus gamma xy cos 2 theta, which in terms of the double angle 2 theta reduces to, when this, if you use the double angle identity, this will become equal to 1 by 2 gamma AB is equal to ex minus ey divided by 2 into sin 2 theta plus gamma xy divided by 2 into cos 2 theta. The principal strain will be equal to this, and principal plane for a strain will be equal to minus gamma xy divided by ex minus ey. If you remember, for in case of stress, this was equal to minus 2 tau xy. As we know that this half of shear strain is equal to this formula, therefore this will become like this. We may We may construct Mohs circle for normal and shear strain in a manner similar to that for normal and shear stresses. हम जिस तरह shear stress या normal stress के Mohs circle ड्रॉ करते हैं, हम shear strain और normal strain के लिए भी Mohs circle ड्रॉ करते हैं. सिमिलरली जिस तरह हमने पीछे प्रीवियसली इसको पढ़ा कि हमने कैसे Mohs circle को डिवाइस किया था, वो वही इक्वेशंस को यूज़ करके उनको सेपरेट करके एक फॉर्म बनाई इक्वेशन ऑफ सर्कल की, विच कम्स आउट टू बी लाइक दिस. तो आपके पास एक ये फॉर्म बनती है जिसमें रेडियस विल बी इक्वल टू ई एक्स माइनस ई वाई डिवाइड बाई 2 होल स्क्वायर प्लस गैमा एक्स वाई बाई 2 होल स्क्वायर under root. The center of Mohs circle for strain will be Ex plus Ey divided by 2, comma 0, and always on the epsilon axis, which is the strain axis. The strains E1 and E2 are known as principal strains, and shear strain at principal axis is 0. Similarly, you can put the point A, which is epsilon x and gamma xy by 2. Previously, you have used sigma x and tau xy. Here, at instead of tau xy, shear strain will be half. Okay. The similarity in form between stress and strain components is further simplified by the following statement. A Mohs circle for a strain can be transformed into concentric Mohs circle for a stress by means of a scales transformation. You can use the scale transformation. Radius of a stress circle will be equal to radius of a strain circle multiplied by E, which is the modulus of elasticity, divided by 1 plus mu, or center of stress circle will be equal to center of strain circle multiplied by E divided by 1 minus nu, in which R stress and R epsilon are the radii of stress and strain circles shown in figure, whereas OC sigma and OC epsilon are respectively the stress and strain coordinates of the centers of the concentric circle. E is the modulus of elasticity and V is the Poisson ratio. For example, this is tau and half of gamma, epsilon or sigma, a concentric circle. This circle shows the strain circle, and this is the stress circle. Thank you.